Here is a question on general organic chemistry. Read the question carefully and think about the answer. Let us solve it step by step. Let us now begin solving this step by step. We analyze each pair for the nitrogen inversion barrier. Concept: the nitrogen inversion barrier, delta G, depends on the geometry at nitrogen, ring strain, electronegativity of substituents, and steric effects. The transition state for inversion is planar, sp2-like, at nitrogen. Option A. NMe3 versus N-IPR to me. Trimethylamine, NMe3, has a known inversion barrier of 7.9 kcal-mol. Replacing methyl groups with bulky isopropyl groups in N-IPR to me actually lowers the inversion barrier because the bulky groups prefer the planar transition state. They spread out better in a planar geometry, relieving steric strain in the pyramidal ground state. A very low delta G of 0.2 kcal-mol for N-IPR to me is consistent with this steric flattening effect. This data is correctly placed. Option B. N-methylizyridine versus N-methylpyrrolidine. N-methylizyridine has a very high inversion barrier, 20.5 kcal-mol, because the ring constrains the CNC angle to 60 degree, and going to a planar sp2 nitrogen in the transition state would require the ring to adopt an even more strained geometry. The angle strain in the transition state is enormous. N-methylpyrrolidine, 5-membered ring, has a much lower barrier, 7.0 kcal-mol, close to acyclic amines since the 5-membered ring can more easily accommodate a planar nitrogen. This data is correctly placed. Option C. NMe3 versus NCl3, trimethylamine has delta G is equal to 7.9 kilocalories per mole. NCl3, trichloramine, has a dramatically higher inversion barrier, 22.9 kcal-mol, because chlorine is highly electronegative and stabilizes the pyramidal ground state through increased S character in the nitrogen lone pair. The lone pair becomes more S-like in the pyramidal form when electronegative substituents are attached, making the pyramidal form much more stable relative to the planar transition state. This is consistent with the known trend that electronegative substituents raise the inversion barrier. This data is correctly placed. Y, D, is correct. All three pairs, A, B, and C, have correctly placed data based on well-established principles of amine inversion barriers, steric flattening in A, ring strain angle effects in B, and electronegativity stabilization of pyramidal geometry in C. Therefore, the correct answer is D. Therefore, the correct answer is option D.